Good afternoon. My name is Mario Avila and welcome to my seminar-long presentation. For my topic, I ended up choosing to present over the common damage mechanisms in process piping, so let's begin. Engineering roles are usually split between either designing components or troubleshooting certain types of problems. Either way, knowing common damage mechanisms will apply to most industries an engineer can work in, because if you're not troubleshooting and trying to find the root cause failure of a problem, you can use this knowledge to anticipate what operating conditions your component will be exposed to and design around it. This is also important to the industry because you need a sense of understanding between reacting to a problem and planning to prevent it. As you can see in the picture, this is a fire that happened at the 2012 Chevron refinery fire in Richmond, California. And I'm going to use this as an example of the difference of prevention versus reaction. Officials had seen the corrosion in the piping but had no plan to replace it, as they deemed the section of piping good enough to last up to 5 years longer until the date of the next turnaround. The pipe was more corroded than they thought it was, and it led to a leak that burst the pipe, which caused the explosion. The cause of this was corrosion under insulation, or more commonly referred to as CUI, which is the most common damage mechanism in the oil and gas industry. Ultimately, around 15,000 people reported an injury from the loss to the environment, and Chevron had to pay $163 million in fines. So why did I choose this topic? The oil and gas industry is somewhere I would like to start my career in, and I already have internship experience within the field. The troubleshooting process you go through when trying to figure out the root cause analysis of a failed equipment is something that I really enjoy doing and that I'm good at. And all engineers, regardless of their industry, need to know about these damage mechanisms in order to avoid making a mistake in their field that could damage people, the environment, or the equipment that they're dealing with. Corrosion under insulation, or CUI, happens when an insulated pipe starts accumulating water, usually on the underside of the pipe, and starts corroding as a result. This thinning of the bottom side of the wall leads to cracks that weaken the material even further, and eventually starts leaking. Inspection of piping sections are frequently carried out to monitor the rate of corrosion in the pipe, and the standards will tell an engineer what the minimum accepted wall thickness will be for a certain size of piping. CUI is only really found in the range of 120 to 300 Fahrenheit, and it accounts for the majority percentage of a maintenance budget, so it's a big problem in the industry and can lead to accidents and explosions, like the one at the Richmond refinery fire. Common solutions for CUI can be found in metal jacketing of the insulation to prevent water from penetrating the insulation in the first place, or metal mesh covers if the insulation is for any other purpose besides maintaining the temperature of the process. For example, if the insulation is being used for personnel protection, it would be better to install the cage around it to prevent people from accidentally touching it and getting burned. Thermal sprays to coat the piping like a paint job are also available to use, but are significantly more expensive and are only used for more justifiable occasions. If the section of piping cannot be brought out of service for maintenance, then clamps, leak boxes, or wraps are usually installed to mitigate any leaks that formed or might be forming. Graphitization is what happens to carbon steel piping that runs at temperatures higher than 800 Fahrenheit for an elongated period. Steel exposed to this temperature starts seeing the carbon forming nodes at the grain boundaries, so it essentially is breaking down into iron and graphite, which will make carbon steel lose tensile strength and become brittle. This becomes a problem because it leads to more cracking at the walls and in turn leads to leaks of the process. In the graph, you can visualize how three common types of carbon steels used for piping start degrading in max allowable stress as the temperature increases to 800 Fahrenheit, where graphitization begins. Common solutions for this problem include lowering the temperature of a process to reduce the risk of cracks forming or using different materials for the application. Molychrome alloys are usually used in high temperature applications because they don't degrade as fast as carbon steel at those temperatures. You can see A335P1 and P2 denoted by the yellow and green lines respectively, set at 14,000 psi for max allowable stress at 800 Fahrenheit, while the carbon steels all sat below 13,000 psi for the same temperature. Mixing and injection points are used to add reactants into a stream of process. This turns out to be a common damage mechanism because of disruption of the flow and the change in temperature that results from one stream entering another usually damages the material of the piping if it is not laid out correctly. An analysis of a stream entering another from a T-junction on the right explains this mechanism a little better. The velocity of the fluid flow is shown from slow to fast, from blue to red respectively. You can notice how the secondary fluid entering from the top is increasing speed in each simulation. At the very top you can see the secondary fluid enter and dissimulate without a lot of turbulence downstream. In the simulation shown in the middle, the velocity of the secondary fluid is increased and causing minor turbulence downstream of the junction. And in the last simulation, the same turbulence has grown quite noticeably. In this picture, the result of the turbulence downstream from the junction is shown. Too much corrosion will lead to thinning of this pipe wall section and it will lead to leaks. The same applies to having a mixing point close to a 45 or 90 degree elbow, because the turbulence resulting from the fluid hitting the pipe wall at the turn will corrode that section faster than the other surrounding areas. Common solutions for this is to place a mixing point further upstream from a turn in the piping. Simulating results of the CFD software to find the best possible placement of the mixing point, and if the mixing point cannot be changed, then you could update the frequency of inspections on that section of piping to keep a closer eye on the rate of corrosion. Flashing is a phenomenon that occurs in areas where a liquid's pressure drops below the vapor's pressure and the result in vapor bubbles forming in the liquid. Cavitation is when these bubbles collapse and create a microjet that damages a pipe wall by cracking it. Here's a picture of what the bubbles look like when they're forming inside of the equipment, and below is how the microjet affects the pipe wall. Common solutions to this include the type of material you select for the job. If you think a section of piping will be prone to cavitation, you can choose alloys with better hardness rating. When you're designing flow pathways, build with cavitation in mind, especially downstream from many pumps. Or you could use specially designed valves for flow control, like spillback or auto recirculation valves. Here is a flow path designed with cavitation in mind. The fluid travels from the tank to a pump to another area downstream, but if there's not enough pressure from the pump to push the fluid any further, instead of letting the pump get damaged from cavitation, an auto recirculation valve pushes the liquid back into the tank until there's enough pressure for the liquid to continue being pushed downstream. Thermal shock and thermal expansion are concepts you need to keep in mind when running piping with high temperature applications. Most killed carbon steel piping will expand around 4 to 5 millimeters per 100 feet of piping at 300 degrees Fahrenheit. While it may not sound like a lot, the end of the piping will push up against the wall of another pipe or an equipment and create large stress loads that could degrade the pipe. Thermal shock works the same way, but is reserved for cases when a material changes temperatures drastically in a short amount of time. Think about putting ice cubes in a glass container and then pouring hot coffee in there. The sudden contraction and expansion from the temperature change produces a large amount of stress and strain on the glass, and it will shatter it if these forces are large enough. The same applies for materials used in piping. If you are running very high temperatures in an intermittent service line, then it will go from ambient temperature to 300 or 800 degrees in a matter of minutes. For example, a pump out line to a flare. Running these type of lines, you'll need to keep in mind the operating conditions to avoid the thermal fatigue that could result on the material. Common solutions for dealing with these thermal issues is limiting the thermal stresses to the piping instead of the equipment. Thermal stress in the pipe will be easier to deal with than a bigger flange or valve. Use expansion joints in piping to allow the section of piping to expand and contract without as much stress to the material. and plan around leaks in order to reduce them. If you know an intermittent service will be more prone to leaking because of the thermal stresses induced on the piping, then introduce more frequent maintenance inspections on that section of piping. The importance of understanding common damage mechanisms is big. Performing root cause analysis of the failure of an equipment will be easier if you're aware of common damage mechanisms. Following through with preventative maintenance planning will be easier for an engineer if they understand which areas of the piping network are the most at risk. And it is important to understand these topics in order to avoid making a costly or deadly mistake in the engineer's profession. Here is a picture of the aftermath of the BP Texas City explosion, which occurred because of a faulty instrument in a vessel that was indicating a lower volume in the tank than what was actually there, leading to an overflow and a spill that resulted in an explosion. The other picture is the aftermath of the TPC Port Neches chemical plant that hits a lot closer to home for those at Lamar University because they most likely got to see it. About 6,000 gallons of process started spilling out of a fractionator tower and into the environment because of a burst pipe. The result was a vapor cloud forming around the unit and multiple explosions happening. There were no deaths reported and only 3 employees were injured. In conclusion, many of the problems that you will face as an engineer will be because of metallurgy or the operating conditions of the equipment. These topics are not just restricted to the oil and gas industry, so you can take this knowledge with you to any industry and they will still apply. It is also important to know that it is better to understand the problem and work to prevent it and to deal with the loss to the equipment, the environment, or the personnel. Thank you for your time.